Hey everyone, this is a video lesson that I'm using in my EP Calculus AB class. I'm putting it online in case it would be helpful to others as well. In this section, we are going to discuss derivatives of inverse functions, and we'll see a neat little relationship between their values. But then in particular, we are going to dive into derivative formulas for inverse trig functions. If you have watched any of my video lessons in the past, you have probably heard me say things like, I love this section, I love teaching this stuff. You're not going to hear me say that now. It's not that it's bad. It's just I can't get into it. I'm going to try. I'll tell you what, I put off making this lesson for over a week because I was just like, it just is what it is. And here we are now, and I'm doing it, okay? And we're going to try to enjoy it. We are. Okay, so don't stop watching because I'm going to try. Let's try. Let's go. Let's go with the fun little matching thing. I thought this would be a fun little warm-up, so that's why I put it here. Oh, I should say, as usual, there is a link in the description to a set of printable guided notes that you can use that has all of the problems that I cover in the video lesson. Okay, now let's go. Number one says match each function f of x with its inverse g of x. Okay, so what does inverse mean? Well, inverse functions are functions that reverse each other, right? Or they undo each other. Like, for example, multiplying by 2 and dividing by 2, right? Those are inverses. Or squaring and square rooting, cubing and cube rooting, or sine and inverse sine, right? So you could probably match a lot of these just by looking at the numbers that are in f of x and g of x, but you should probably think about why they are inverses, right? For example, let's go with blue. F of x equals 2x minus 7. Its inverse is going to be this one, right? G of x equals x plus 7 divided by 2. Now, let's talk about why they're inverses with some algebra. Okay, whenever you have a set of inverses, whenever you compose them, take the composition of them in either order, what you should get out of that is x for them to indeed be inverses. So if I take f of g of x, and that means this entire function is going to go right in there for the x in the f of x function. So it looks like this. There's minus 7, bring along. And I simplify that, I should get x. Do I get x? Yes, I do, right? These multiply to 1. I then have x plus 7 minus 7. These add to 0, and the result is x. Now, technically, you should check g of f of x as well and make sure that when you take 2x plus or 2x minus 7 and sub it in right here, you also get x. I'm not going to write that out. I think we can see that that would happen, and so therefore these are definitely inverses. Okay, I would encourage you to pause the video at this time and try to match up each f of x with its inverse g of x, and then come back to me and I will have the answers for you. And I'm back, and I have all of the matches. How did you do? Hopefully pretty well. And again, I don't expect you to really write out all of the checking to make sure that you get x whenever you compose the functions, because you could probably tell just by scanning which ones matched up as inverses. Okay, so that was just a little quick exercise to get to know what inverses look like. Now I want to talk about their derivative values, and this is something that's kind of a little fun. Okay. Let's look at number 2. If h of x equals x cubed, then what is h inverse? The inverse of cubing is cube rooting, right? So we can say that h inverse of x, by the way, this little -1 superscript is a way that we can denote an inverse. It is not, in this case, a power. It's not a -1 power. It is just a notation to show that this is the inverse of h of x. And we will say that the inverse of h of x is the cube root of x. In number 3, we're asked to calculate h of 2. Okay, calculating h of 2 means subbing 2 in to the h of x function where we see x. And so that's 2 cubed, which is 8, right? Next question, what is the corresponding ordered pair for the inverse? Well, one thing about inverses and ordered pairs is that they're switched. The x's and y's are switched, meaning if this is an ordered pair, 2, 8, okay, again, this means we have when x is 2, oh no! Sometimes there's like this little button on here, and I don't really know what the buttons are for. I wish they wouldn't be there because I've never needed to use them, and every time I click them, something bad happens. So sorry, I had to pause the video for a minute. Okay, here we go. When x is 2, y is 8 is the ordered pair that we get from h of 2 equals 8. Now, what is the corresponding ordered pair for the inverse? Okay, for the inverse, well, that would just be this ordered pair switched around. When x is 8, look at this. When I would sub an 8 into the cube root, what do I get out? I get out a 2, right? Y is 2. And so that's a property of inverses. Their ordered pairs are switched. Okay, and now what we want to dive into here is what does that look like in derivative values? Okay, so let's move on to number 4. Calculate h prime of 2. Okay, that's not so bad. H prime of x, I'm just going to make a little note out here. H prime of x is 3x squared by the power rule, right? The derivative of x cubed is 3x squared. Now, let's find h prime of 2. And to get that, we would take 3 times 2 squared. 2 squared is 4. 4 times 3 is 12. There we go. We got it. Okay. Now, in number 5, we're asked to calculate h inverse prime of 8. And although maybe that doesn't seem related to what we just did up here, keep in mind that if x is 2 for h, then 8 is the x coordinate, this y coordinate, sorry, it's just like, did I see something weird there? The y coordinate 8 is the x for the inverse, okay, is this right here, okay, it's coming from that corresponding ordered pair. All right, so here we go. Let's calculate, okay, this notation is going to look weird, but what we need to first calculate is h inverse prime of x. Weird, right? We have parentheses here and here. H inverse prime, that's how you show that. And for that, we need to use power rule again, right? Because the cube root of x is x to the 1/3 power. So keep in mind, we could rewrite this as x to the 1/3 power. And now to get its derivative, we use the power rule. 1/3 comes down in front of the x. You subtract 1 from 1/3 to get your new power, and that is negative 2/3. And from that, we will calculate h inverse prime of 8, sub 8n for this x. 1/3 times 8 to the negative 2/3 power. All right, you're not expected to be able to do that without a calculator, but it's actually not that bad. It is the cube root of 8 squared. Okay, the cube root of 8 is 2, 2 squared is 4, and it's all negative, so it's in the denominator with this 3, and so we would have a 12 in the denominator. So this would be 1/12. Woo! All right, now take a look at this little question in the box. What is the relationship between these values? Take a look at what we have here. When we calculated h prime of 2, we got 12. When we calculated h inverse prime of 8, which is its corresponding x value for the inverse, we got 1/12, and those are reciprocal values, right? Reciprocals. And that's actually something that happens with all of these inverse functions' derivative values. So moving on to the next page, there is a little try this that looks tricky. Okay, given that f of x and g of x are inverse functions, with f of 5 equal to 3 and f prime of 5 equal to 2/7, you are asked to find the value of g prime of 3. What? Like, you're not even given any information up here about g. Oh, except that it's the inverse of f, right? And notice that you have a 3 in your G prime, and that is the y coordinate that comes out of this f value. F of 5 is 3. Okay, so what do you do with all of this? Right here, look at this. 2/7, flip it. Because of that inverse relationship, you can take the f prime of 5 value, f prime of 5 value, and flip it to get your g prime of 3 value. Yay. Okay. So let's summarize a little bit about inverse trig function or inverse functions, and then we will move on to inverse trig functions. Okay, so in a little summary, we can say a couple of things. First of all, we can say that inverse functions reverse or undo each other. Now, the notation that we typically use is a -1 superscript on our function like this. Okay, but also I want you to know that anytime you see arc, ARC, and you will see that sometimes with the trig functions in particular, like arc sine, arc cosine, that means the same thing. Okay, it means the inverse function. Or in some cases, I've even seen the wording anti. For example, one time I was covering a chemistry class, and I was just like browsing through the chem book because I used to really like chemistry at one point in my life. And so I thought, oh, I want to look through this. And there were some problems that were using the natural log. And at one point it was showing how to solve an equation with a natural log in it, and it said to use the anti-ln. That was the wording in the chemistry book, anti-ln. And so I took that back to my calc students the next day, and I said, hey, your chemistry book here is telling you to use the anti-ln. Do you all know what that means? And there were some confused looks, and I said, it's E, right? E is the inverse to the ln, your e to the x function. And so, we have that wording as well. You'll actually also see that wording when we talk about going backwards with our derivatives, and we will do things called anti-derivatives. It sounds so much fun, doesn't it? They are so much fun, and I'm not being sarcastic. I love anti-derivatives. Okay, but anyway, for right now, I just need you to know that you could see all of that different notation just for inverse functions. Okay, now to find an inverse function, this is kind of important to understanding what you're looking at when you're looking at a graph of an inverse function sometimes. To find an inverse function, it has to be able to be a function. That's an n right there. Inverse function. And so that actually means that it must be one-to-one. To find an inverse function, you have to have one-to-oneness. I'm just going to say it must be one-to-one. And one-to-one means that whatever graph you're looking at of whatever function you're dealing with, it has to pass both the vertical line test and a horizontal line test, meaning if you draw a vertical line through your graph, it only touches at one point, and if you draw a horizontal line through your graph, it only touches at one point. Okay, so again, it has to pass the vertical line test and the horizontal line test. And so this might mean that your domain may need restricted. Okay, and let me just show you what I mean by this with sine. Okay, so if I look at sine of x, and I'm just going to do like a zoom 7 trig viewing window. Sine of x passes the vertical line test, of course. However, it does not pass the horizontal line test. If I were to draw a horizontal line through different parts of the graph, I could touch in more than one place. And so to get the inverse sine function, we restrict the domain to just a portion of the graph where we know it will pass the horizontal line test. And so that's why when you look at the graph of something like inverse sine, let's take a look what that looks like. You don't see much, right? You just see this little section, okay? And that is because we restricted the domain of our sine to get an inverse function, for it to be a function. Okay. All right, and then finally, the last little thing I want to put here is that if you have two functions that are inverses, then their compositions result in x. So we'll say if f of x and g of x are inverses, then f of g of x equals x, but so does g of f of x. Okay, so that's some information about inverse functions in general that would be good to know as you continue your study of calculus. What we are going to look at now in particular are the derivative formulas for inverse trig functions. And let me tell you why. For a lot of inverse functions, like this example, we already know how to do the derivatives. If I give you x squared and you know that its inverse function is the square root of x, you already know how to do the derivatives of both of those functions, right? All of these functions, we know how to do the derivatives of the f of x column and the g of x column, right? I'm not saying you want to do it. I'm just saying you could do it, right? Okay, so, we don't really need to dive into derivatives of, those types of inverse functions. What we do need to dive into, because they are kind of crazy, just going to warn you, are derivatives of inverse trig functions. Before we go there, though, let's just review what are the derivatives of these 6 trig functions. The derivative of sine is cosine, right? Maybe you want to pause and see, test yourself. Can you fill out this column right here? You should be able to, okay? And then come back to me. I think I'm going to do the same thing. I'm going to pause. All right, I'm back. Check your answers. How did you do? Were you able to get every derivative, just off the top of your head? Okay, if not, don't beat yourself up, but keep in mind that we've already discussed all of these. What we need to discuss now are what are the derivatives for their inverses. And I'm going to warn you, they're going to look really different. Okay, so let's talk about why. We are going to use implicit differentiation and some identities to formulate the derivatives of the inverse trig functions. Okay, so before we do that, let's put some important identities in here that we need to know. These are 2 Pythagorean identities. Okay, the first one hopefully sounds familiar. We're going to need to use at some point the Pythagorean identity that sine squared of theta, I'm going to use the variable theta, plus cosine squared of theta. You could use any variable in here. I'm just being fancy. Equals 1, right? That's equal to 1. And actually, what I'd want to do with this is I want to solve this for cosine theta. So picture that. You would subtract the sine squared theta and then square root to get rid of the power of 2, right? And so cosine theta is equal to the square root of 1 minus sine squared theta. We're going to need to refer to that form of this Pythagorean identity in our first derivative proof. So I want to have that there. Okay, another Pythagorean identity that we're going to use is this one. And this one, I don't know if we've looked at it very much, if at all, this year. So let's just write it and just know that it's an identity that we will be using. Secant squared theta is equal to 1 plus tangent squared theta. That's just another Pythagorean identity that we will need in our second derivative proof. Not a second derivative, our next derivative proof. All right, so let's do it now. Take a look at this. We are going to be doing the derivative of arc sine. Another way of saying that is the derivative of inverse sine. And so what you have as a starting point here is that function. Let y equal inverse sine of x. And we are going to try to differentiate it. However, you can't just say, I'm going to differentiate it, because we don't know what the derivative of inverse sine is. So our first step is to rewrite this in terms of sine. How do we do that? Like, take sine of each side. Okay, if y equals inverse sine of x, then that means that sine of y equals x, right? That's a way that we can move the sine function to the other side. When we do that, it changes from inverse sine to sine. Now we will differentiate. So I'm going to write here, this was a little rewrite step. Now I am going to differentiate with respect to x, and that is going to need implicit differentiation, right? The derivative of sine of y is cosine of y times dy over dx. Because we just took the derivative of a y, we have to multiply by dy over dx. On the other side, the derivative of x is 1. Solve now for dy dx. Dy dx equals 1 over cosine of y. And we just did it. We just did the derivative. Not so bad, right? Not so bad. However, this is called the y form. I don't actually know if that's what it's called. That's what I call it. I call this the y form of the derivative. And it's not used often. And every year I have a hard time convincing students that they need to do this next part, because they say, hey, that kind of makes sense. The derivative of sine is cosine, so the derivative of inverse sine is 1 over cosine, but it's of the y. Okay, yeah, it does make sense, kind of, if you think about it. However, I mean, it really makes sense, actually. Like, to me, it really makes sense. But we don't like to use the y form. And I have a hard time of convincing you. I'm just saying, though, as we move on through solving problems that involve the derivative of inverse trig functions, and even when you move on to higher level calc, you're going to want to see this other form, and you're going to want to know this other form of the derivative. Okay, that's the best I can do. That's the best I can say. Okay, so there's more to this. All right, and here's the more to it. I'm going to write a note over here. We have this Pythagorean identity that I wrote in red, and I'm going to take this part of it. Cosine of theta equals the square root of 1 minus sine squared theta. However, instead of having a theta there, I can put that, any variable I want. So I'm going to put y there instead. Cosine of y is equal to root 1 minus sine squared of y. Okay, and we got that from that Pythagorean identity. Okay, so what does that do for us? Well, notice that we have a cosine of y here. So we could rewrite our derivative equation as 1 over root 1 minus sine squared of y. What the heck does that do? That just makes it look even more complicated, and still in terms of y, it's still a y form. I know. However, look at this. Sine of y, we have it defined to be x, right? This equation is now going to come in handy. Where you see sine of y, you can change it to x, or where you see sine squared of y, you can change it to x squared. So one more rewrite of our derivative and we're done. with the derivative of the inverse sine, I promise. It is this, 1 over root 1 minus x squared. And this is what we call the x form of the derivative of the inverse sine. That's what I call it. And it is the one that is used as we move through calculus. Okay, this one is not really used ever. Yeah, okay, so let's write that in here. 1 over root 1 minus x squared. That's the derivative of the inverse sine. 1 over root 1 minus x squared. Ta-da, there it is. I'm going to do one more of these with you where I completely prove it, and then we just sort of take the other ones and say, okay, let's just assume it's good. So let's now do the derivative of our tangent, or we are starting with the function y equals inverse tangent of x, and we want to find its derivative. We're going to find that derivative by rewriting as tangent of y equals x. And then we are going to differentiate with respect to x using implicit differentiation. The derivative of secant squared, or I just said it, the derivative of tangent is secant squared. The derivative of tangent of y is secant squared of y dy over dx. The derivative of x on the other side is 1. Solve for dy over dx by dividing both sides by secant squared of y. And there is your derivative. Not so bad, right? In y form. Again, though, this is not what we typically use. We're going to write a note, and the note is this Pythagorean identity. Now, in this form, it has thetas in the trig functions. We're going to put y's there. So we're going to write secant squared of y equals 1 plus tangent squared of y. Note, secant squared of y equals 1 plus I can fit a t in there. Tangent squared of y. Okay, so you see this secant squared of y, you are going to replace it with 1 plus tangent squared of y, because this equation tells you you can do that. So our derivative is now 1 over 1 plus tangent squared of y. That's still y form. Let's move to x form now, because we have this equation right here that says tangent of y. Oh, you can change that to x. That's what that equation says. It says, oh, hey, look at this. Tangent squared of y, you can change to x squared. And there's the derivative of the inverse tangent of x in x form. Whew, we got another one done. So I'm going to write that one in right here. 1 over 1 plus x squared. Okay, for the next one that we do in the sequence is the derivative of arc secant. But I'm just going to tell you that I'm going to skip a whole bunch of steps in explanation to try to keep this video sort of short. I hope you're okay with that. If you're not, you can reach out to me and ask me about this, and I'll tell you more. But again, I'm just going to sort of do my quick little rewrite, my quick little implicit differentiation step. The derivative of secant is secant tangent. Oh my gosh, what did I forget? Oops. Secant y tangent y was good. But I need to dy over dx right there, right? It's the end of the day here. I'm a little bit tired, to be honest. Okay, so dy over dx is 1 over secant y tangent y. And I usually have my students, at least somebody always says every year, but okay, like, can we just stop there? I know that one. Like, that, I get that. That makes sense to me. And I'm like, yeah, I know. It's the y form. It, does seem right. All right, but it's not. Except this time, I'm not going to go through notes and an explanation because it has to do with restricting domain, and there's all sorts of little nuance to this explanation. I'm just going to go for it and tell you, here's the x form. It's a little wild. It is 1 over the absolute value of x times root x squared minus 1. There it is. Again, if you want to know more about why that came to be, you could Google it or reach out to me and I will gladly give you a better explanation than what I'm doing here. Okay, so I'm going to write that one in as well. Inverse secant is 1 over the absolute value of x times the square root of x squared minus 1. Woo! Remember I told you these were going to look very different than these ones. Yeah, they do. So there you have it. You have the three main inverse trig functions that we derive via implicit differentiation and trig identities. Now, as for the cofunctions, to derive those, we can actually use this pretty nifty little identity that helps us get to them quickly. Okay, and it's this. The inverse cosine of x is the same thing as pi over 2 minus the inverse sine of x. So what that means is if you want to find the derivative of the inverse cosine of x function, you can differentiate this and get it. And we already know the derivative of inverse sine, right? We just found that one. We already know the derivative of pi over 2 as well. What's that? That's 0, right? That's a constant. The derivative of pi over 2 is 0. We're going to subtract from that the derivative of the inverse sine, which we proved to be 1 over root 1 minus x squared. 1 over root 1 minus x squared. So therefore, the derivative of the inverse cosine of x is just equal to negative 1 over root 1 minus x squared, right? 0 minus 1 is negative 1, and you have this denominator. Woo! That was not so bad. Let's fill that into our table. Here it is. The derivative of the inverse cosine is the same thing as the derivative of the inverse sine. It's just negative. And you can do that with the other inverse cofunctions as well. Oops, I went too far. I'm not going to go over all of these. I'm going to pause and write them in. Maybe you want to pause and see if you could write them in for yourself as well, and then come back to me and we'll have them all filled out. Here they are. Inverse cotangent of x can be rewritten as pi over 2 minus inverse tangent of x. That is just an identity. And therefore, the derivative of inverse cotangent of x is just negative 1 over 1 plus x squared. Same thing can be done for inverse cosecant of x. It is pi over 2 minus inverse secant of x, and then we take the derivative and we get negative 1 over the absolute value of x times root x squared minus 1. All right, so let's finish up by writing those in our table, and we'll have our table done. Here it is. Let me go to blue. Inverse, these are in a weird order. Sorry, inverse cotangent of x is down here, and it goes with this one. So it's negative 1 over 1 plus x squared. Inverse cosecant of x is right here, and it's negative 1 over the absolute value of x times the square root of x squared minus 1. So if you know 3 of them, then technically you know the other 3, the cofunctions, because they are the same thing, only negative. Finally, for problem-solving purposes, I will hopefully ease the anxiety a little bit by telling you that these four are the ones that we typically see in AP Calculus 8B. Okay, so I always take out the inverse secant and the inverse cosecant from the list of things that you're going to need to know and use. And we're just going to use the derivatives of inverse sine, cosine, inverse tangent, cotangent. And really, remember, these are the same, just differ by a negative, and the same thing for these ones. Now, I put this in u form, meaning u is a differentiable function of x, and that just is going to show that usually when we differentiate these inverse trig functions, we need to use, there's so many bells around here, we need to use chain rule. Okay, so if we have inverse sine of u, the derivative is, I'm going to use my red because that's what I've been using for inverse sine. It is 1 over the square root of 1 minus u squared. But u is a differentiable function of x. It could be like x squared in here. It could be x cubed plus 1, anything in terms of x. So we have to multiply by the derivative of u with respect to x. And again, that's just showing chain rule in the formula. Inverse cosine will be the same thing, only with a negative 1. Inverse tangent is 1 over 1 plus u squared times du over dx. And inverse cotangent is the same, only negative. Okay, so now let's finally, last part of this little video, let's use this, use these formulas in some examples. We are now ready to do example 1, just now. Find dy over dx. All right. So the derivative, which you can denote as dy over dx or y prime, is coming from the derivative formula for the inverse sine of x squared. Now, for the formulas that you just wrote in the table above, your u is x squared. So wherever I see this u, I'm going to replace it with x squared. So I have 1 over root 1 minus x squared squared. Don't forget about this part, though. We need to multiply by the derivative of the u. So we're going to multiply by the derivative of x squared, which is 2x. Cleaning it up a little bit, we can take our power to a power here, and we can multiply that 2x with the 1 in the numerator. So here's what the final answer could look like, cleanly written. 2x over root 1 minus x to the 4th. Ooh. So as long as you know this formula or you have it to refer to, it's actually a fairly easy derivative process. It's just subbing into the formula, really. Okay. All of the hard work that we've done through this video is understanding, getting a basic understanding of inverses and proving these formulas that we can now use. Let's try another one. Let's try B. Here we are going to take the derivative of inverse cotangent of x cubed plus 1. Again, that x cubed plus 1, that will be the u in the formula for the inverse cotangent, which is down here. Negative 1 over 1 plus u squared is the start. So dy dx is equal to negative 1 over 1 plus x cubed plus 1 quantity squared. Then don't forget chain rule, multiply by the derivative of the u with respect to x. The derivative here is 3x squared. Now, I always have students ask, well, how much do I need to simplify? How much do I need to simplify? And this is one of those cases where I'm like, I kind of hate that word in this case, because what does simplify mean? Does simplify mean expand x cubed plus 1 squared into x cubed plus 1 times itself and FOIL and combine like terms? I mean, what's the purpose of doing that? Is that going to do anything for us in this example? No. So just leave it. 1 plus x cubed plus 1 quantity squared. It's just fine like that. In my opinion, I would not do the work of squaring and combining like terms here. You can if you want to, but I would leave it like that. One more, everybody. One more. We are almost done. Example 2. A particle moves along a horizontal axis that is positioned at any time t greater than or equal to 0 is given by x of t equals inverse tangent of the square root of t. The question is, what is the velocity of the particle when t equals 16? Velocity. Okay, so to get velocity, we need a derivative of the position function, right? A little bit of review of our rectilinear motion there. So we're going to take the derivative of this, and that will give us the velocity. And to do that, we need to use the derivative formula for the inverse tangent of u. This is the u, the square root of t. Okay, we can do that. Here it is. It's 1 over 1 plus u squared. 1 over 1 plus this squared times the derivative of this, which is 1/2 t to the negative 1/2. Okay, now again, let's talk about simplifying. I mean, if you were doing this without a calculator, for sure, you would want to do some manipulation there to write that in a better way to be able to evaluate when t equals 16. Keep in mind, we still need to do that. So, you know, you might want to do some moves like, well, first of all, the square root of t squared is just t, right? We could put 1 over 1 plus t right here. And then what do we do with this? Well, the 1/2, okay, could become a factor of 2 in our denominator. This 1/2 could just go boop, boop, right there, like that, boop, boop. And the t to the negative 1/2 is a square root of t in the denominator. So, you know, you could do that simplifying for the purposes of being able to easily calculate v of 16. If it's calculator allowed, though, I mean, taking this form and subbing 16 in when you see where you see the t's, you know, is going to work just as well. All right, so what do we have here? We have 1 over, this is 17 times 2 times 4. Which is 1 over 136. Did I do that in my head? No. I have an answer key right here. Yay, we're done. Okay. As I stated a little bit ago, all of the hard work that we did in this video was really just to get to a point where we can sort of feel good about having these formulas and understanding where they come from. Really, most of this section is all about understanding that these formulas are out there, and sometimes we do need to use them to differentiate. And so, you know, be aware of that as you move on in your study in calculus. I hope this video was helpful. Bye.